One of those boards. All right. Thank you everyone for coming to the second PCB workshop we have this semester. So hopefully you guys remember some of the stuff that we went on from last time where we went over kind of more of the design of the PCB more than actually really doing anything in the software yet. So we kind of went over briefly the kind of desired outcome, what we wanted from the project, what we might need externally, had a little block diagram that we drew. And then we went over some system requirements that we wanted for our PCB. And lastly, once we had our system requirements, we then were able to pick out the specific hardware that we wanted for our project. So last time, I believe I pretty much went over most of the hardware, which included a motor driver, different connectors that we're going to have for the motors and batteries and control, and as well as just briefly went over current sense. And then these are the specific motor that I had planned for this breakout board. And again, this can change depending on whatever motor you want to use. But I decided to kind of build it around this specific motor. That's simply because that's the exact motor we used in Micromouse. So it's something I'm familiar with. Then we looked at some battery, and then we have just microcontroller of your choice. So today we're going to get into actually doing the schematic for the design that we came up with last time. And to start that off, we're going to start off with just the motor driver. So that's kind of one of the biggest parts of this build. So essentially, you have picked out a motor driver. If you remember last time, we went on DigiKey and put in some certain requirements that we had made from our system requirements, and we're able to find a bunch of different motor drivers that might work for our specific case. I chose this one just because it was one I was familiar with, and also something that I liked to, it's just something that I personally liked when I went off. But a lot of those motor drivers would have worked. So, first thing I want you guys to do is just go to DigiKey's website, and we're gonna find the data sheet for that specific motor driver. So once you're on DigiKey's website, go ahead and type in what you see at the top. If it's too small, I can increase the size. I'm gonna do that really quickly. All right. So that's the specific motor driver that we had picked out last time, which is the DRV 8231 DDAR. So once you have that typed in, just go ahead and hit enter. And that should bring you to the exact part number that we plan on using today. And if you haven't quite typed it in, it's still up here in the top. So once you have a part picked out, or if remember we went through the process to find it, you'll might click on that part and it'll bring you to this screen, which will show you, for example, how much is in stock, how much it is, and a quick description of it as well. And these are all things, you should pay attention to is pricing and how much they have in stock. But the main thing that we're going to be looking at here is the data sheet, which includes a bunch of information regarding to the specific chip and is going to roughly tell us how to use it. Down here, there's also some just extra information regarding that chip, but I'm going to go right into the data sheet. So down here where it says data sheet, you can just click that and it should open up this PDF. Um, so With the PDF open, you'll notice there's a lot of pages. There's 44. That's a lot of pages to go over. Obviously, you don't want to sit there and read 44 pages of a motor driver data sheet. That sucks. But the reality is, you do need to skim through a lot of it. Because there's a lot of specific little quirks and features of all these different chips that might have a an effect on your design and everything like that. And so it's ideally to try to skim through the whole thing, but I'm going to kind of go over some of the main points that we want to look at when we go into our design. So, just gives us, features and a quick description talking about what this chip is. I stole that little diagram that we used last time off this data sheet. Um, we scroll down the table of contents. There's a couple main things that I want to look at here. Um, so the down here we'll see the pin configuration and functions. This is really important for initially when you're starting to understand, okay, what does pin 1, 2, 3, 4, 5, 6, 7, 8 do? What are those different pins and what do they do? So that's going to include all of that information. The specification is also kind of related to that system requirements that we went over. For example, if you have a system requirement for a satellite and it needs to be in a specific temperature range, this is where that information would be held in the specifications, where it would see, okay, this chip can withstand negative 40 degrees Celsius to 120 degrees Celsius. And you're like, all right, good, that fits our range. Or this also includes that same information we were looking at before. What's the voltage input? What's the different ranges that we can have? All of that information, again, comes back from our system requirements. So we want 5 or 3.3 volt logic or control, and we need the motor input to be around 8.4 volts. So if we go into here, which is the specifications, you'll see a bunch of different things and they're kind of ratings for stuff. These are the absolute maximum ratings, but more than likely below it, it will give you kind of the recommended ratings for everything, which is what you should strive to hold everything at. So the recommended ratings is in between 4.5 and 33 volts. If you remember, we had 6.4 and 8.4 volts. So that's in between our minimum and maximum. The nom in the middle just stands for nomial, and that's essentially just what it kind of desires to be at average. But for these ones, they don't really have it can be anywhere in between that range, and it's happy anywhere in between that range. That's why it doesn't really have a nomial value right there. So, the reference voltage or the voltage for the logic, if you remembered before, we were talking about 3 or 5 or 3.3 volt logic. That's going to be right here, that reference voltage. And if you're unfamiliar with that reference voltage is, you can always right, logic input range. Okay, that one. So logic input range should be around 0 to 5.5. That reference voltage is also 0 to 5. So both of those kind of have to do with the logic, but both of those fit within our requirements. So it could either be 5 volts or 3.3 volts. Both of those fit in that range, so we should be good. PWM frequency, this is something we're going to get into a little bit later, but this is, if you remember last time, PWM were just those kind of squares that you can modulate the width of the pulse, which is pulse width modulation. And they can run at different frequencies. So this just states that. Peak output current, we have the peak output current of 3.7 amps. And if you remember last time, we went and looked at the specific motor that we had. This was the specific motor that we chose to design it around, and we noted that the peak current is less than an amp. So that also fits into this. So the peak output current can't be, it's between 0 and 3.7, which in this case, it's only 6.7. So good. These are all things that we kind of roughly went over last time. But again, you should double check in the data sheet to make sure that that chip can actually fill out the requirements that you want it to do. So here's kind of the thermal things that I was talking about. This is some heat dissipation, which we're not going to get too much into. But it's going to include a bunch of other information. A lot of this is is stuff that you'll become a little bit more familiar with as you read more data sheets and do more designs. I don't have the time to go into a lot of these, and a lot of these we're really not really going to need. But as you read through more data sheets and get a little bit more familiar with these systems, the rest of the kind of parameters will make sense. So I'm going to go back up to table of contents. Oh yeah, this is the thing that I was talking about before, the pin configuration and functions. Remember, that was the first thing I said in the table of contents you should look at. So this includes the chip that we're going to be using, which is this one. You'll notice that there's also another chip right here. These are both the exact same chip. They're just packaged differently. This one's a little bit smaller, even though it looks bigger. It's a little bit smaller and has the pins underneath of it. This one's a little bit bigger and has the pins on the outside. So you can see here that we have eight pins, and from this we can try to figure out what each one of those pins does. So pin one, that's ground. That should be fairly straightforward. In one and in two are things that I briefly went over last time, talking about the direction. If you remember, I was talking about motor driver H bridges. Um, yeah, I kind of showed something that looked like I showed something that kind of looked like this, where we talked about how you can change the direction and speed of the motor. Um, And so those are those two gates or switches. Last time I had one with switches. This is just the same thing, but with MOSFETs, which is a little bit more accurate to what's actually inside the chip. Um, and so I talked about what in one and in two were, and those were just the things that controlled this switch, Q1 and Q4. So these two switches would be on, and these two would be off, so it would flow through here, and vice versa. If these two are off and these two are on, it would flow through here. So, in one and in two are the controls for those pair of switches, Q1 and Q4, or Q3 and Q2. So controls the H bridge output, has internal pull downs, but um, the next one is iSense. So that is a current sense. We're not really going to be using that in this case. It essentially allows a pin to have a current sense measurement on it. But we're not going to be using that for our specific case. But if you are curious about it, go read the data sheet, look this up, and you can try to find designs that do use it. Out one and two are going to be the H bridge output. So that's going to be connected directly to the motor or other inductive load. Um, and then VM, so that's the voltage for the motor. So that's the 4.5 to 48 volt power supply. And then it mentions that we should connect a zero point 0.1 microfarad bypass capacitor to ground, as well as a sufficient bulk capacitor rated for the motor voltage. So that right there is something, if you're not familiar with designing PCBs or something like that, we'll be like, whoa, what is, it's a lot of new words and kind of, what is a bypass capacitor or bulk capacitance? Um, so both of those things are actually very straightforward, and we'll go over to designing those in a little bit later. But yeah, we'll talk about them a little bit later, but I promise you they're really not too bad. And again, if you're doing this on your own, you could easily kind of look this up and try to find solutions too. So VREF is a analog input, which is just a voltage information on current regulation. It's sort of to do with the logic. I don't think this explains it too well there, but I believe in this section it might explain a little bit better. And then pad, that's the giant pad on the bottom. That is just a big pad to get rid of heat. You could think of it like if you ever see heat sinks on computers, they're like these big metal you might have seen things that look like that before on chips or computers, where they look like these big metal slabs that have everything cut out. Those are for the purpose of getting rid of heat. And that is the same exact purpose for this giant metal pad on the bottom. It's just a big surface area to get rid of heat. You could think of it as, if you have your phone and you're trying to get rid of, like, if you're using it too long, it'll get really hot or something like that. How do you cool it down? Oftentimes, if you have something flat, you could put against this a little bit colder. It will spread that heat out across it a lot better. So some people, hold it with their hands or something like that to try to absorb the heat. That's the same idea with this big thermal pad. It's just a big piece of metal to try to get rid of the heat that is produced in that chip. So I'm going to go back to the table of contents. So we have a rough idea of what the pin configuration functions are. So we know what pin does what roughly. Um, we also went over the specifications to make sure it'll work for our specific case. Um, and already that's like, close to 10 of the 40 pages. So it really shouldn't take too long to try to skim through this. Even though it looks like it's going to be a lot, usually you can kind of get through a data sheet within an hour or two, and you'll have a much better idea of how to do your design once you've done that. And when you can actually sit down and really read it, it makes a little bit everything seem a little bit more clear. Obviously, this is harder because I'm quickly showing it to you on the screen, but I do recommend you guys to go through and try to read some of this afterwards. So, this again, I would highly recommend just kind of looking through the detailed description, which includes a bunch of pictures, including what's exactly happening inside of the chip when we're using it. So the H bridge are these for MOSFETs right here. Um, and it doesn't really look like an H bridge. They're just placed in different locations, but that's what it is. It's an H bridge. And here is our motor outside of that. And then right here is our in one and two, which are used to control the speed and direction. And then here's our VM with that 1 microfarad capacitor and the bulk capacitor that was mentioned earlier. Remember, it said, recommend to add those. In this functional block diagram, it includes that bulk capacitor, which they don't give us a value, and a 0.1 microfarad capacitor. Um, so, again, I'd recommend kind of going through and reading through things like this. Gives you a lot of insight on the design, but due to time, I'm going to kind of skip through some things. So, remember, it didn't give us a specific capacitor value to put right here. If you see down here, we have CVM2, which is that capacitor right there, the capacitor VM2. The first one is just that 0.01 microfarad, and it recommends a low ESR ceramic capacitor. If you're unfamiliar with what ESR is, it is electronic series resistance, and it's a fairly straightforward concept. Basically how much resistance is that capacitor represent. And it doesn't mean it actually has resistance, but as you increase the frequency, it might show some resistance there. And so this is a concept I'd also recommend just briefly looking into. If you're unfamiliar with what ESR is, and it's just saying that the capacitor is rated for the voltage for the motor. So, for example, capacitors also have voltage ratings. Noted that at the top of ours, we had all these ratings that we had right here. So we can't go above 33 volts or 5 volts there. Capacitors also have those ratings, and certain capacitors will have lower ratings and other ones higher. So we shouldn't choose a capacitor that's only rated for, let's say, 8 volts if we're going to be applying 16 volts right there. Now this part, so this gives us a thing to check out for how we go about choosing that other capacitor right here, that bulk one. And it says section 10.1. And if we click that right there, there's going to be a ton of information going over how to choose that bulk capacitor. Um, and it might, sometimes they give you specific equations for things. In this case, it's just kind of giving a general recommendation. I chose just like a decently high value. I didn't, and I chose a decently high value just because it doesn't really recommend anything specific in this case. So I just chose something that's a little bit high. And so that sheet recommends. Yeah, it says testing is required to determine the appropriate size bulk capacitor. I just chose one that was decently large and called it a day. But theoretically, if you're doing like, a very high level design, you would attach your motor, be able to test out different capacitors and measure different values. But in our case, we could just choose a high value and it should probably be fine. All right, so the last thing that we're going to be looking at is kind of a cheat to go through this data sheet. Almost all data sheets of chips provide you with something that is going to talk about the application and implementation. So this is something that can kind of fool a lot of people that are getting into PCB design for the first time because they'll note that hey, if I click here, it's going to give me a um, a block diagram here, and hey, it has everything that I need. Now that we have a value right here for that capacitor. It's 47 microfarads, and it has 0.1 microfarads, and there's a small resistor right here. And a lot of times, people who are new to PCB design might just kind of take all those values and directly move it to their schematic, which oftentimes will work, but sometimes it won't because this, for example, in this specific application, there's a small resistor right here. And if you're unfamiliar with what this resistor does, because maybe you haven't read the full data sheet, you would throw it in there assuming that you need it. However, this is for the current sense, the I sense. If you remember, I was talking about we're not going to be specifically, we're not going to be using the motor driver's current sense, like a kind of pin right there. And so we're not going to need that 0.02 ohm resistor right there. So in our case, we're not going to have this specific resistor, but I'm likely going to choose a capacitor value similar to 47 microfarads. Um, that just is a high enough capacitor that I'm like, I can kind of call it a day on. Um, and so right here, it gives an example layout for a system that has a 12-volt motor. The average motor current is 800 milliamps or zero point 0.8 amps. The startup current is 2.1 amps. The motor stall current is 2.1 amps. The trip point. So it gives us all this different kind of information given right here. As well as the PWM frequency. And if we have a motor that that runs at 12 volts and fills out all these same requirements, great. But reality is, for example, our motor has a average current of 70 milliamps. That's way smaller than 800 milliamps and doesn't have the stall current is 0.6 amps. And in this case, they have a motor with a stall current of 2.1 amps. So these give example parameters for things that might fit the general application, but I would still highly recommend you go about kind of not just coming to here and trying to kind of copy what they have here, but go through the design process of, okay, why did they choose zero point 0.2 ohm resistors, or why did they choose a 47 and a 0.01 microfarad? And there might be some other component that we might want to add. Um, so oftentimes you'll get all of those questions answered in the data sheet. So, now that we kind of went through roughly what we have planned for um, we have our chip and we have a kind of example. Um, we have our chip and we have our system requirements. We're now going to, and now that we kind of have a good understanding of roughly what the chip is doing, I'm going to move back over to Altium and we can start actually placing things. So I'll give you guys a second to get up to Altium. Is everyone out over at Altium or you need another second? All right. So, if you remember last time, we kind of put this rough schematic down and we had made sure to use um, net labels, and we also showed you how to kind of move things around using the space bar or using X and Y to flip things around. And also, if you press Control W, you can automatically make your wire setup. So we kind of went over a lot of the basics of Altium last time. This time we have a design in mind and we want to start putting on the schematic. So the first thing that we're going to do is we're needing to add that motor driver into the schematic. And you might ask, how are we going to make that whole motor driver into the schematic? And there's a couple different ways to do that. The first thing I'm going to show you guys is if you go into the bottom right corner and click panels. It's kind of hard to see on the presentation because it's all shifted over a tiny bit. But in the bottom right corner where it says panels, you're going to see this thing that says manufacturer part search in the panels. So go ahead and click the manufacturer part search. So the manufacturer part search is basically a giant library full of parts that Altium has already created schematic symbols for. So first thing we need to check is if the specific chip we chose has a schematic footprint or a PC or a schematic symbol and PCB footprint. So that same chip that we were looking at earlier, which is oh my God, there it is. The DVR 8231 DDR, you can go ahead and click that little thing right there. That'll copy it. And once you've copied the part number, you could then move over back to Altium and paste that part number into manufacturer part search, hit enter, and now we have, oh, I thought this was, all right. So, that's funny. I thought this one had models. Huh. All right, guess not. We're going to be creating our own schematic footprint, which is the next thing I'm going to be showing you. If you're lucky, I thought this one had a model. That was my bad. But nonetheless, I was going to show you both methods either way. But this one, you'll notice right here, there's a big little chip with a line through it saying that models are missing. Now, just for an example, this is another chip that I've used. Hey, is it BNO005? There it is. This is another chip that I've used a good amount of times. And if I click in the name for that chip, you'll notice that there's no line through that little chip symbol. And all I can do is I can either right click and click place, or I can hold it and drag it over to my project. And now I have this schematic symbol right here. And if we double click it or go into the properties, you'll notice down here in the parameters, it'll show that there's a footprint assigned with it as well, and there's a 2D and 3D view of that. So, since the chip that we had chosen, I just want to had a model, but since that one doesn't have a model, we're going to go ahead and create it. And I'm going to delete this. So, over to the right, remember last time we added libraries into our project. So we included the PCB library and as well as the schematic library, correct? Um, so now that we want to start to move to create the schematic symbol first for our chip. So I'm going to double click the library right there on the right hand or on the left hand side. So that library we added last time, the one that says schematic library, we're going to double click that and it's going to should open up something like this. And then now at the bottom right or bottom left, you'll see that there's projects and also the schematic library. So you'll see right next to projects, there's the schematic library right there. And this is the library that we added, and here are all the parts for it. Just out of curiosity, I wonder if it was, okay, it was not in that one. So, we're gonna go ahead and create a new schematic symbol for that chip that we just found for our motor driver. So, if you see right here, there's gonna be an add button. You can go ahead and click add and the component name. So let's go ahead and you can paste the name that we had copied before. So that's the name of the chip that we're going to be creating. All right. So it will then bring you up with this empty schematic sheet. So there's absolutely nothing here. This is really annoying. Once you're here, we need to start actually adding the chip's kind of schematic symbol. You could go about and start placing blocks and pins and everything else like that, but Altium has a tool that makes it pretty easy to generate chips. So if we go ahead and click Tools at the top left, and then there's Symbol Wizard right below it. So we're going to click, so in Tools, we're going to click Symbol Wizard. And then that opens up this panel right here, which includes, you'll notice that there's already some pins right here, and it has a layout style. So we need to choose basically what the style of our schematic symbol will be. We're gonna keep it dual inline. So that is what the chip is. This is a dual inline package as well, just because there's two of them in line. So I'm going to choose it to be dual inline. And how many pins do we have? We have a total of 8 pins. So I'm going to move over here and just add 8. So now we have a couple different things, and this is this is a half decent schematic symbol for that chip. So position is the position of the pins. Um, the display name is basically what's going to display next to it, and the designator is the actual pin itself. So if we go back to the data sheet, And let's say we just look at the application information. And I'm going to go ahead and duplicate the data sheet so I can have two of them open at the same time, and I'll show you why here in a second. So the application, so if we scroll up to, there's two things that we would like to use. So right here is like, this kind of looks like a general schematic symbol, right? So I would kind of want to kind of on the replicate this on the schematic. So I'm gonna go ahead and see here. So ground is pin one, in two is two, in three is one, vref is four. And over here, it's in the same order. And over here, so, oops. Out two, I send out one VM. Whoops. This something's annoying. Out two, I send out one VM. All right. I personally might switch some of this around, even though that the actual pin numbers is, one, two, three, four, 5, 6, 7, 8. I kind of want to move some things on the schematic symbol just so it's a little bit easier to draw. For example, preferably would like the power to be close to the top and the ground to be close to the bottom, just because, in my opinion, that makes sense because power is, going up and ground is going down. So I think I'm gonna try to move the VM and the vref to the top and keep the ground and ISEN at the bottom. So I'm not physically moving those pins. I'm just moving where they are on the schematic. So I'll show you here. So you'll notice that there's the display name, the position, and the designator. This is, oops. So again, the position is what position the pin is in the schematic symbol. And if I want to change the pin, it's going to be the designator right there. So, for example, I want the VM and the vref to be in the top left corner because to me that just makes sense to have power at the top. So I'm going to go ahead and put the position one as VM. And if we remember, oh my gosh, move to the bottom. If you remember, VM is pin five. So I want to move that to position one. So if I go back here, position one, I'm going to change the designator to five. So now pin one or pin five is associated with that first position. And the display name, I'm going to name it VM. So boom. So pin 5 is up at the top and it is the display name VM. I also want the vref to be also at the top. And you can maybe have it on the top of the right side, but for me, I'm just going to have it right below it. So vref, and what pin is that? That is vref is pin 4. 4. I want the inputs to be on this side, so I want in one and in two also on that side. And those pins, I believe, are two and three. And I'm just going off memory, but I'm gonna double check. So in two is pin two, and in one is three. Now on the right side, I think I would like the motor out two and out one at the top and I send and ground to be at the bottom. So I'm going to start with out two. So out two is pin 8. And if you'll notice too, the order goes 1, 2, 3, 4, 5, 6, 7, 8. So if I want it to be at the top on the right side, I need to go all the way over here and do out 2. And that is also pin 8. So I don't need to change the designator on that one. but out one, I want to have out one right below it, and that's pin 6. So right below it is out one. Change the designator to 6. The last two that we have is the ISEN and the ground. We'll do all caps. And I forget what pins are that. So ISEN is 7 and ground is 1. ISEN is 7, ground is 1. All right, so I'm going to leave it here in case you guys got a little bit behind when we were filling out the pins. Um, The next part is kind of optional. It's more so just kind of visual. If you want to change the out two and out one to be outputs, all that's going to change is there's an arrow on the schematic symbol. I don't know if you could see it right there. Now the arrow for out two and out one are pointed out, and the other ones are pointed in. So this is something that doesn't matter too much, but visually it can be nice. I'm just going to change these ones to be outputs. So once everyone has gotten to this place, oh, whoops, sorry. All right, has everyone been able to copy those? All right. So we now can place our we can place our symbol, and that's going to go ahead and now appear in this um the new schematic thing that we just added. So we just added the DVR 8231 DDR, and this is going to be placed right here. Personally, I don't like to have the pins this crammed together, so I'm gonna go ahead and open it up a little bit. So you can take that yellow box, open it up, and I'm gonna move everything so there's like a space of at least 2 in between them. And I might have made it too big, but I can change that in a second. And be careful not to click this, whoops. You could always control Z. Um, but sometimes you can click just the number and it might only move the number. So if you click the pin, which is that line right there, then it'll move that. And I'm going to change the size like this. And I might expand it a little bit. Um, Now, if you want to grab multiple things, you can obviously drag and grab certain things like that. And there's two ways to do it. So if you drag and pull left, you'll notice the box is green. And if you drag and pull right, the box is blue. So if you drag and pull green, anything that it touches will be selected, and I can move them like that. However, if you go the opposite and drag and pull blue, the only things that are selected are the things that are completely encased in that blue circle. So if I go like this, it's not grabbing anything because it's not complete encasing anything till I go over them. Now I've completely grabbed them. So, they're useful for different purposes, but just wanted to mention that. So once you're here, there's a couple more things in the schematic symbol that I want to add before I add that into my project. So the first thing I want to add is if you go ahead and click properties on the right-hand side, and if you don't see properties right there, you can go into panels and open properties there. But once you click properties, there's going to be a couple things right here that I would like to add information. So the first thing I want to add is the designator. The designator essentially is just which chip this is. And you might not be familiar with schematic designators yet. You'll get a little bit familiar with them as you go on. But for example, resistors are Rs, capacitors are Cs, inductors are Ls. Um, connectors are J, switches are SW, and chips like this one are designated with U. So if you're not familiar with what it is, you could always just kind of Google what's the designator for like a chip, and it should be able to come up, or a connector or anything. But you can type U, and the next thing you want to type is a question mark, because there could be 30 different chips on our board, and we don't know which one it is. So if we keep it a question mark, we can actually autofill all of those chips at the end. Next is the kind of comment. So the comment, I'm going to go ahead and basically just copy the design ID in there as well. So that is now going to be in there as well. And lastly is the description. So the description, I would like to be able to know what this part is, even if I don't know what that number is. So a good way to fill out the description is to go back to, like, let's say DigiKey or something like that. And if you see down here, there's a detailed description. And normally, if I'll just kind of copy that and paste it into the description. So we can go back here, paste, and now if someone just clicks on this and doesn't know what it is, we know it's a bipolar motor driver NMOS, PWM 8 SO power pad, which is a lot of stuff. But once we have all of that added, um, I'll go ahead and now save it. So if you can do Control S to save, or you can click the top left and click save. But normally I'll just do Control S, and now this part is now added into the schematic library. So, um, is everyone up to this point? So, this point. All right. Cool. So I can go back to projects. So on the bottom left, we've been in the schematic library. So let's move back to projects and then open up the schematic symbol again, or the schematic document. So once you're here, you can go ahead, and if you have anything that we did last time, you can go ahead and select it all and delete it. We're not going to be using it. Um, but you can go click panels and then up to components. So this is going to include all the libraries that we have. So in the components, we're going to go up to this top thing and click the schematic fills lab one. And that was the library that we were just in. And now if we pay, oops. Uh, Now if we copy, I'm going to copy the part number again, and move back here and do Control V. We'll notice we now have this part. So again, you're going to go into panels, open up components. And once you're in components, you're going to choose the Phil's Lab library and then paste that chip ID that we had chosen. And now we can go over here and move it into our project. And now we have something that wasn't in any of the libraries or anything like that, but we were able to use. And you'll notice the chip name is on the bottom, and then yeah, everything else is there. Did I think I messed up on this one a little bit. I noticed that the pin is inside of the object a little bit. I don't know if you guys did that, but I'm gonna go ahead and fix that on mine. So if you go and double click the library again, I realized that maybe I Control Z'd it, but I'm gonna move it like that because the pin numbers were hidden before. So if you make a mistake like that, you could just come back to the schematic library. For that one, I moved it back and just Control saved it. And then now when I come back to it, it'll be updated like that, but I messed up. Cool. All right, that looks better. All right, so now that we have our motor driver right here, we can kind of start going through the design process. So, if you remember, I'm gonna go ahead and use this as like a general kind of thing and start by connecting some of the um, connecting and naming some of the stuff. So I'm gonna just do Control W to create that wire, and then go ahead and do this. And this is the V motor. So remember last time we were able to place those ground ports. This time we're going to place a power one. So you can just do place bar style power port, and you can place it there. And it says ground right now, but we can go ahead and change that. So create a little wire and then right click the this right here. It should be a ground thing. And then you could do place bar style power port, and I just placed one connected to that right there. And once I have that there, you could double click it or again go into the properties. And then we're going to go ahead and change the name to VM. So that is, I'm going to name it plus VM just because, oops. So this is the positive for our motors. Below that, we have our voltage ref. Um, and I'm just going to do a line out. And then if you remember the net labels that we were using before, I'm going to go ahead and choose a net label, and I'll just label this one. Um, I'll label it VREF. And I'm going to go down and do the same for a lot of these. So um, this in one. I'm just going to copy that, Control C, Control V, and then change that to N2. Now, if you remember, I'll give you guys a second to get to this place. Actually. All right. All right, so hopefully by now you have this kind of roughly laid out. And I'm going to go back to the data sheet. And if you remember, VM had these two capacitors right here, which was the zero point 0.01 microfarad capacitor and the 47 microfarad capacitor. Um, if you're not familiar with capacitors or kind of have used them before, oftentimes you'll see in labs and stuff like that, there will be different sizes for capacitors physically. You'll see some smaller ones and they might get bigger and bigger. And as they get bigger, their capacitance also gets bigger. The same applies here. meaning that we have a limit to what size we can choose for these capacitors. And if you're unfamiliar with roughly what size works, what you could do is you can kind of go back to DigiKey. Oops. Uh, you can go back to DigiKey, and if I just type in right there, I'm gonna type in ceramic capacitor. And the reason I'm doing that again is on the data sheet, they recommended to use a low ESR ceramic capacitor. So if I kind of just type in capacitors, you'll see these ceramic capacitors right there. And again, we have 600,000 options. Um, but let's just start off with the kind of the first one, which is the zero point 0.1 microfarad capacitor. So this is 0 0.1 microfarad capacitor. We have 10,000 options, which is ridiculous. But now that we have chosen this, if we scroll over to the right a little bit, we can see the different sizes that we can get them in. So this looks like we can get them as small as 0201s, which if you guys have your PCB ruler from last time, has all of these sizes. So if you remember 0201 was that tiny grain of sand size resist or like a package. And it looks like we can get them in 0201 and we can get 237 different types. So in this case, we don't really have a small size problem with the zero point 0.1 microfarad. However, if we go up and if we're using that 47 microfarads that it also recommended, if I click 47 microfarads right there, and then scroll back over here to the package size, you could see 0201, there does not exist a 47 microfarad 0201 capacitor. It looks like the smallest I see is 0603. But if I click that, there's only 38 options. And if we want to get a little bit more precise, so we want it to be 20% or 10% with the value of 47 microfarads. Um, oops, there might be, okay. Yeah, so it looks like we can get a 47 microfarad in the smallest of 0603 size capacitance or size footprint. But more than likely, I would like to choose something a little bit bigger than that, like 0805 or even 1206 or 1210. So I normally like to choose something a little bit larger than the smallest option because usually the smallest option has a very wide range of tolerance. So it might say 47 microfarads, but it might also say like 30% tolerance, meaning that it could be 30% less than 47 microfarads. And it is technically intolerance, but 30% is kind of a significant amount in my opinion. So I would like, let's say, to run that 10%. So in 10%, yeah, so the only 10% ceramic capacitor that we have for 47 is 1210. We lost the option for 0603 and 0805. So it looks like the smallest capacitor that we can have that is 47 microfarads and within 10% of 47 microfarads is 1210. So we're going to move back here and we're going to replace our capacitors. So again, we're going to go into panels in the bottom right, go to components, and keep having to move all these things. But, we're going to come back to the components and we're just going to search cap. And we're going to see a bunch of different physical size, different capacitances. So if you remember last time, I said that 0603 would be the smallest that I would choose for kind of hand soldering. And let's say we're assuming that. And the zero point 0.1 microfarad had plenty of options. We were not limited to by size. So I'm just going to choose 0603 because that's what I'm comfortable with here. So I'm going to choose it and I'm going to place it, I'll place it right there. The next one I want to choose is the 47 microfarad capacitor. And remember, we could not find a 47 microfarad capacitor with 10% tolerance less than 1210. So 1210 is going to be the next one on there. So we have an 0603 capacitor and a 1210 capacitor. And those are just the physical sizes of the capacitors. Again, if you have your PCB ruler, it'd be nice to reference those kind of sizes. I can pull it out here. But next, I can double click on that, and there's a couple things that we have there. So the designator is just C question mark. We don't want to mess with that quite yet. But for the comment, I'm going to place the size of that capacitor. So the 1210 was the 47 microfarad capacitor. And I'm not going to add the farad because it's a capacitor. We should know that it's in farads. But I am going to add the micro. And for this one, it's the zero point 0.1 microfarad. However, I would recommend instead of doing zero point 0.1 microfarad, instead name it 100 nanofarads, which is the same thing. 0.1 microfarad is equal to 100 nanofarads. The reason for that, again, is just trying to get rid of any of the dots in the comments because they can sometimes get lost if you're making a bill of materials automatically and stuff like that. So we'll just keep it as 100 nano and 47. And if we go back to this, we could see that both those capacitors are connected to ground. Hey, open up. All right, so I'm gonna go ahead and I'm gonna move them like this. Again, space bars to flip them around. And I'm gonna make a ground symbol. So I'm gonna, click that ground symbol up there. I'll place it maybe a little bit down here. And then you do Control W and just connect like so, which is, oh, whoops, not like that. Like so, which is the exact way that we had it, the exact way it was hooked up on the recommended schematic. So if we see here, we have the motor, and then we have these two capacitors in parallel. Um, I might move this over here just so visually it looks a little bit closer to the other one. Oops. And again, that is that same idea where we have the positive and negative. Obviously, the negative's hooked up to ground, but we have this schematic here with the correct capacitor sizes chosen. And personally, for me too, I also kind of like to hide the ground symbol or the ground name. Obviously, this is a ground symbol. I feel like we don't need the duplication of ground right underneath of it. So I'll often click this little eyeball and hide it. It just, in my opinion, makes the schematic a little bit cleaner because everyone should know that this is a ground symbol. Um, I don't need to have ground, directly underneath of it. All right. So, the next thing we want to do is I'm going to go ahead and connect both the ISEN and the ground to ground. And I'm just going to copy this. So I'm going to click that, Control V, Control C, Control V, classic stuff for that. And then we also have our out. And we're just going to leave them as is and add some net labels on them. Oops. Two. I'm gonna do an underscore on these ones so it's a little bit easier to read. And I'm going to do an underscore on these ones as well, just because I want to. And then if it's kind of off placed, so you'll notice if you're placing like something like a net label, you'll have that bottom left thing where that's where it selects it and it moves the text kind of out the wire. You can change the justification and that will change its position. So anything like that. I'm just going to move it to the opposite side so it's over the wire. And again, you can just double click it and then move that. All right, so if you're at this point, I'm gonna go ahead and like we said, we wanted to control two motors. So I can do something as simple as, you know, select everything. So if you select everything like that, you could do Control C, Control V, and now all of a sudden you have two motors, but there now becomes an issue that we have the same net names on certain things. So out two is going to be connected to that out two, but we don't want them to be. We want them to go to separate motors. So, unfortunately, for the things that are not consistent across these two, like the ins and the outs, I'm going to go ahead and have to change them to, let's say, motor one in one. So that's motor one. And do the same over here. So motor one in two, motor one out two. And this one's going to be motor two. And that is our schematic for the motor drivers. Just gonna move it up right there, but we're done with the schematic with the motor drivers. Now we can move on to, let's say, things like what do we have next? You know, if you're kind of get to different stages like this and you're like, well, I'm not really sure what to do next, that's why we have our system requirements. So it's a really useful guide to just come back to and say, okay, um, the hardware includes that chip, and then we have motor connectors, control logic, more reference logic, or these are all just connectors as well. So we have all these different connectors, um, as well as the current sense chip. In the I think before I want to kind of move away from this chip, I kind of skipped over something that I would usually recommend doing at the same stage of setting up your schematic symbol. If you remember the last time I pulled up the other chip and I opened it up or double clicked it and scrolled down and showed you kind of that 3D model that was in there and it had the footprint beneath of it. Obviously, this one we created ourselves, but we haven't added that PCB footprint below it. So, we need to add the PCB footprint as well. So, instead of going to the schematic library, I'm going to go into the footprint library. So I'm double clicking that. It might take a second to load because there's a lot of information in the PCB library. But unlike the schematic symbol, the PCB footprints are kind of more general. You could think of it that you've probably seen chips that look like this, and they aren't this exact chip, right? You might have seen a chip like that on any of your other boards, and they look roughly like that, but they're not this exact chip. And the reason for that is there's general chip sizes just as there is general resistor and capacitor sizes. So if you look on your ruler that you should have gotten last time as well, you'll see next to the chip sizes and everything like that, there's some general footprint sizes. So if you look at A right there, where it says 8, so just to the left of your chip and resistor sizes, there's a bunch of things that say, A, D, B, C, G. Those are also general kind of footprint sizes for chips. So, for example, A is for an 8 SOIC. Um, this one is a 8 SO power pad, which is a um, the specific kind of footprint for this. And you'll notice that this one is the package or case is an 8 power SOIC. So the only difference that this is a power and versus something that isn't a power, if you'll notice on A, that is the exact footprint of this chip, except for the pad. Oh my gosh. If you remember up here, where is it? Right here, we had all those pins, but there's also that thermal pad underneath. The only addition to this footprint is the thermal pad underneath. You'll notice that there's no big metal pad underneath this, the A. So if we go into our footprint library that we should have kind of open by now, which is right there. I want to look for that specific kind of footprint because there's a good chance in this library there's an 8 SOIC and it might even be a power pad. So um, if I just do 8 with this 8, oh come on, SOIC. Okay, here's an SOIC 8. And there's a couple different other ones. This SOIC 8, the one that's in here though, um, should be roughly what we want. Um, but before I kind of copy and make another one that's SOIC 8 power, um, I want to make sure that this will actually work. So in the data sheet, you'll oftentimes, you should be able to have a layout. So this will give you kind of information regarding that PCB footprint. The last thing we just created was the schematic symbol. Now we're creating the PCB footprint of what it's actually going to look like on the PCB. So I'm going to go to layout, um, scroll down a bit, and here is the actual kind of layout down here. So here's an example board layout. Above is the physical layout of the chip. We're not so much interested in that. We're more interested in what it wants for the example board layout. So this is also called Power Pad SOIC, and it's going to give us a bunch of information regarding what it wants the PCB footprint to look like. And so I'm just out of curiosity. There is not that power pad. Okay. SOIC. Yeah, yeah, it looks like this one is also over them, and I think the fact that it's not an SOIC, I feel like it's going to be very different values. But for this one, I'm gonna go ahead and measure what we have here and measure this and see how close it is. So, for example, this has, let's figure out the units first of all. I believe it's in millimeters. That would make sense because it says millimeters up top. Okay, I'm assuming this is all in millimeters. We'll double check here in a second. But it looks like the pad size for the average one is 1.55 millimeters by 0.6 millimeters. And over here is the kind of PCB footprint and stuff. And I'm going to measure out what this pad, or actually, I can double click it and open the properties and see the kind of sizes for it. And for the X size, so that's that one. So zero point 0.6 and it's by 1.45, which is very close to this. Um, which is nice. Honestly, I feel comfortable that it would probably work with 1.45 as well as 1.55. Usually there's like a tolerance that they might give you. So a tolerance of you know, zero point 0.1 millimeters or something like that. But this one should probably work. So the next thing I need to check is make sure that the pads are separated from each other at the same distance I want. So the distance between each pad is 1.27 millimeters. And the way to check that is you can press Control and then M for measure, and you'll see this green thing start to come up. And when you do Control M, this is going to start to come up, and I'm going to go ahead and choose the top layer. So this is a little bit of the PCB design aspect of it, but these are just the different layers. And if I press 3, you'll see that there, we have this chip here. Um, but if I press 2 on the keypad, I'll go back to this view. So I'm going to do Control M to measure it, and I'm gonna try to get right in the middle of that. And because I can't really get to the direct middle of that, I'm gonna make sure I'm on the top layer of the thing that I'm interested in clicking. And then I'm gonna press G, and I'm gonna go ahead and change my grid size. Right now it's at 0.25. I'm gonna move it to zero point 0.1 so I could just get a finer grid. So if I do Control M, and now it'll go right in the middle, and you'll see that green circle appear, letting you know that you're right in the middle of it. So if I click that and go right to the middle of that, they are 1.27 millimeters across, which is exactly what this one is set up to be. And the next thing I'm going to check is the distance apart from one another. So 5.45 millimeters. And over here, it's 5.4. The fact that it's zero point 0.5, I think should just be fine. Um, they're very close. So I can use this design other than the fact that it doesn't have that pad on the bottom. So the only thing that I'm going to add is that pad. But before I do that, I don't want to mess with this specific footprint too much. So I'm going to go ahead and add a new one, and it'll basically just bring you back here, and it's gonna be empty. um, but I'm gonna name it. So if we go into properties again, uh, hey, and you go into footprint. So if you go into properties and then footprint, this will have the name of that footprint, and I don't want to name it the exact chip. I want to name it what the footprint is. So the footprint is um, mm, mm, it's a 8 power SOIC. And just to keep it the same, I'm going to do power SOIC 8, just so it's the same. Um, Same format with this one that has 8 at the end of it. And the description, we can keep that empty for now. But I'm going to go back to this one and basically just copy everything that is here because we know that it is roughly what we want. Now, before you can copy things, you'll notice that if you're working on kind of more the PCB side, if you press Control C, it'll instead just bring up this green, arrow thing. So it'll be asking you where you want to copy it from. So if you click this, it'll copy it from the center. And when I paste it again, it'll be, have it in the center. But if I Control C and choose it from the bottom corner, when I paste it again, I'm going to move it from the bottom corner. I'm I think I'm probably just gonna hit it from the center, just cause. And then I'm gonna search up that same one. It was power SOIC8. So that's the one that we just created. And then click in there and then do Control V. Wait, where is it? Oh, I'm way zoomed out. Whoops. So I went and pasted, you know, this into there. And now all we need to add is that power pad on the bottom. So we're going to have this metal pad right here, and I need to figure out the size of it. It looks like it's 3.4 by 2.71. So there's a couple different ways to place components. So there's placing a pad, which will place something that has a designator, and a designator meaning that this has a actual like a pin associated with it. So, for example, if we had the designator 11 on the schematic symbol that we just created, it will be connected to that right there. But I want to instead use, place a via, which is essentially just a hole in there, and it sounds interesting, but we're going to be changing that. And this doesn't have an associated pin with it. Since this one is just a pad on the bottom to get rid of heat, it doesn't really matter if anything is connected to it. So once we have placed a via, so it's going to be up here, you can click that, place a via. You're going to see this thing, which essentially is just a hole. And we're going to change the template. Okay, so we have none of those. All right, that's fine. We can change it down here. So, once we have placed that via, we can, go ahead and double click it and open the properties. And we want to change some of the things. So we don't want it to be something that all goes all the way through the board here. This red is the top, that gray is through the board, and that blue is the circle. I don't want any of that. This is not going to be simple hole size, and the hole size I'm going to have 0. Um, and then I'm going to get rid of the bottom layer as well. So now all we have is kind of this pad on the top layer. And so we're going to need to change its thing. I don't want it to be a circle. So I think where's it at? Where's it? Oh, there it is. Yeah. No, never mind. Yeah, normally they have the shape right there. All right, well, I could make the other one then. All right, well, we'll just make it a pad and get rid of the designator. That works too. So designator, we could just basically get rid of. Um, so now it doesn't have any designator. We're gonna change this to, I mean, instead of doing that, I could just use template, huh? These ones actually have the templates. Okay, this is what I was looking for. So there's a bunch of different templates right here. The R's are like just general kind of shapes. You should be able to see a good amount of these templates. So once we have placed a pad, so I'll kind of restart since I was all over the place. I went and placed a pad, and after I placed a pad, I double clicked it and went and changed the template. I changed it specifically to any of these, but it doesn't matter too much because we're going to be changing the size of it anyways. Um, okay. So the X size, um, which is actually this size, so that's going to be 3.4 millimeters by 2.71. So 3.4 millimeters by 2.71. And I know, oh, I got them mixed up, huh? So that's 2.71 and 3.4. Okay, cool. And you can change it to be kind of exactly a square or slightly rounded edges. Um, I'm going to keep it similar to this, just slightly rounded edges, but it doesn't have that much. Um, you can change it to be 10%. I'll do 5. It's just how round the corners are. Um, so now essentially we need to place that directly in the center of um, the chip. So to do that, I'm gonna copy or I'm gonna move everything, and I'm gonna try to move it right into the center of that. And you'll know you're at the center when the top left it says X00 and Y00. So you can see it right there. The center is at X00, Y00, and then I could try to click the center of this and line those two up. So I believe, go ahead and save this. So I know we're a little bit over time and I kind of rushed a little bit at the end, but if you guys need some help right now, I'll kind of walk around and then, but this is pretty much all we need to do for the PCB footprint. At this point, we are done. Um, I can go through the process of adding it into the schematic, but since we're over time, I can kind of do that next time because it only takes like a minute or so. But I would like you guys to at least get to this point and save, so we could be ready to use this next time. All right.